In this next module, I'm going to talk about the normal approximation to the binomial. So whenever you have a binomial distribution, you might have noticed in the earlier modules that a lot of the binomial distributions, when you do out all the probabilities and you plot them, they look an awful lot like a normal distribution. So it turns out that as long as you're on a binomial where n times p is greater than 5, that is, the expected value is greater than 5, it usually looks an awful lot like a normal, and we can approximate that binomial, those binomial probabilities, with a normal distribution. Let me just remind you of some of the examples that we saw. So for example, we saw this one in the upper left-hand right corner was the wrinkle study. N here was 10 patients. P was 0.5. That exactly gives us an NP of 5. And P times P is equal to 5. Hey, that looks pretty much like a normal curve to me, right? That's very close to a normal curve, of course, with jagged edges, but still very close, and N times P is just 5 there. When we flipped a coin 100 times, N times P was equal to 50, and that one looks very much like a normal curve. When we flipped a coin just 5 times, n was just 5 and p was just 0.5, so this one is n times p is less than 5, but it still looks kind of like a normal curve. And this one over here, we had 8 cases, and n equals 8, and our p was 0.6, so n times p was 4.8. It's a little less than 5, but it still looks kind of close to a normal. So we're able to pretend essentially that we're on a normal curve and calculate probabilities as if we're on a normal curve. What's the mean and the variance of that normal curve going to be? Well, it's just going to be the mean and the variance of the binomial. So it's going to be n times p will be the mean of the normal curve, n times p times 1 minus p will be the variance. So we can literally just view it as a normal curve. That normal curve will have a mean of n times p and a variance of n times p times 1 minus p. So let's just do a little practice problem to illustrate this. So let's say you're doing a cohort study, and the probability of developing disease in the exposed group is 25%. Let's say you sample 500 exposed people, and you want to make sure you're going to get enough people that develop the disease. So you might want to know things like, what's the probability that I'm going to get at most 120 people developing the disease? Well, we're on a binomial. This is a binomial. Each person, there's 500 people, each person has a 25% chance of developing the disease. Am I going to get enough cases of disease, or could that I get 100, less than 120 or 120 or less? Well, the way to solve this, once you recognize it's on a binomial, would be to calculate the exact binomial probabilities of getting all the way up to 120. That would mean the probability of getting 0 cases of disease, 1 or 2 or 3. You'd have to go through and by hand calculate each one of those individual binomial probabilities. Well, that's extremely tedious, and of course you're never going to want to do that by hand. Of course, a computer could also do it for you nowadays, but in general we are just going to avoid that, and instead we're going to say, well, hey, I'm close enough to a normal curve, so let's just pretend we're on a normal curve with a mean of 125, that's 500 times a quarter, and a standard deviation of the square root of n times p times 1 minus p here is 9.68. So I take the standard deviation and the mean from the binomial, and I pretend I'm on a normal. And now if I want to know what's the chance of getting 120 or less, well, that's the area to the left on the normal curve of 120. Now that's below the mean, so we know that that area is going to be less than 50%. I calculate my z-score. It turns out to be negative 0.52. I go to my chart, I look up the probability to the left of negative 0.52, it's about 30%. So I have a 30% chance of getting 120 cases or less. So rather than having to calculate all those individual binomial probabilities, I can just look at it as a normal. And it turns out that normal approximation underlies a lot of the statistics that we're going to be talking about later in the course.